we're going to talk about scale factor, and this is going to be our M2, M3 unit. So we're going to talk about how we can use scale factor, right? How much something is increased or decreased by, right? Enlarged or reduced, and use it involving 2D shapes. So scale factor, right? We've talked about scale a bit in past courses, is the idea of how much we are either increasing or decreasing everything in an image, right? So we're going from one thing to another, right? How much are we multiplying, right? Or dividing each dimension by. So we have a couple of formulas for this. And again, the terminology is just kind of to help you think about specific scenarios. We don't use many variables in this unit. So scale factor is how big is our diagram divided by how big is our actual, right? So this is we use this kind of terminology, especially when we're talking about things like maps. You may have seen a scale on a map before, right? How big is it on the diagram? How big if I was actually to measure on a physical map between Calgary and Edmonton, divided by the actual measurement. How far is it in real life to travel from Calgary to Edmonton, right? And that's the scale factor. That tells us how much the map has been scaled down so that you can hold it in your hand instead of having to drive 3 hours. We also use terms like new measurement over old measurement, right? Or over original measurement. It's the same idea, right? Just some different terminology, just to make sure we know which direction we're going. So this first example, we want to determine the scale factor going from diagram A to diagram B, and the direction is important, right? If I want to go from A to B, well, we notice B is actually smaller. So what I'm going to see is I'm going to see a scale factor that's less than 1, right? I am reducing the size, so I'm multiplying by something smaller. However, in the second scenario, which we'll get to, we notice that from A to B, we actually increase. It's an enlargement. So we're going to see a scale factor that is larger than 1. So if I want to go from A to B, right, I want to go from, technically A could be considered my actual, B could be considered my diagram, right? Or A could be considered my old, B could be considered my new. My scale factor here is going to be the value of B divided by the value of A. And when I say value, I need to make sure I'm comparing like things, right? Think about the idea of how would A and B be similar shapes? If I'm comparing this 12 centimeter length, right, of this rectangle, I want to compare that to the 10 centimeter length of B because that's the short side on both of these rectangles. If I wanted to look at it differently and compare the 24 centimeter side, that width, I would compare it to the 20 centimeter side, the width of B. I don't want to say suddenly that the longest side of A is being scaled down to look like the shorter side of B because that's not true. Right? If I'm scaling this shape, I'm still saying that the length here is like to the length here. Right? And the length here is like to the length here. So I could use either, right? Let's go with the smaller numbers. Let's deal with 12 and 10. So my scale factor is going to be the new, right, which is B on top, and the old or the original, which is A on the bottom. So I have a scale factor of 10 divided by 12, which again, we can express this in a lot of ways. 10 divided by 12 is the same thing as 5/6. This would be kind of a ratio or a factor, scale factor. I could turn it into a decimal. 5/6 is 0.83 repeating. Okay. As a percentage, if I multiply that decimal by 100, it's 83%. Right? So B is 83% of the size of A. It's less than 100. It's smaller than A was to begin with. Right? But all of these are ways we can express our scale factor. The factor itself, right, the fraction, or the decimal is probably most common, but we can always get to a percentage as well by taking that decimal and multiplying it by 100. Right? That idea that if I'm looking at a scale factor of 3, it's wrong pen, right? That's the same idea as increasing something by 300%. If it's 3 times as large, it is 300% of the original size. So let's look at the second example for a minute. I know my scale factor, again, is going to be B, which is my new shape, over A, which is where I started from. And again, as long as I'm comparing similar sides, I'm okay. I can compare the 15 to the 5. I could also compare the 9 to the 3. Right? But I cannot mix and match. I cannot compare the 3 to the 15 and the 9 to the 5 because those aren't scaled equally. I'm going to go with the bigger numbers this time just to mix it up. So my scale factor is going to be 15 over 5. And again, just like our example, the scale factor is 3. Right? It is 3 times as long in this direction, right? 3 times 3 turns into 9. It is also 3 times as long in that width, right? 5 times 3 turns into 15. So it's increasing. Each side is increasing by 300%. All right, let's look at a couple more examples. Oops. Lock that in place. There we go. What is the scale factor and the percent going from A to B, right? So they're telling us the width of Donald Duck here. And again, as long as I'm comparing the width from A to the width from B, I can find my scale factor. Going from A being my old on the bottom to B being my new on the top, it's 7 over 2. I can leave it like that. I can also turn it into a decimal. It's 3.5 times as wide. I can also turn that into a percentage. It's 350% as wide, which means it's also 350% as tall, but we don't have that measurement. Triangle A to B. My scale factor is, right? And as long as I'm comparing the same sides, we talked about triangle congruency, right? These are side, side, side congruent in the sense that one has just been scaled up compared to the other. If I wanted to compare hypotenuse to hypotenuse, I could do that. A is old on the bottom, B is new on the top, right? It's okay to have fractions. It's okay to have numbers smaller than 1. That just means we have a reduction. We're going from something larger to something smaller, right? And the direction does matter. My scale factor here is 1/4, which is 0.25, which is 25%. I can also give you the scale factor and ask for something else, right? In these formulas, we have room for 3 things, right? We have room for a scale factor and we have room for 2 measurements, my actual and my diagram, right? Or my new and my old. As long as I can fill in 2 of these 3 things, I can solve for the third. So here we have Mickey Mouse. Right now it has a width of 3.5 and a height of 2.75. We want to make a new drawing that is a scale of 0.2, right? So it's going to be smaller. Because my scale factor is less than 1, that's a reduction. It's going to be smaller. If my scale factor was larger than 1, it's going to increase. It's an enlargement. If my scale factor is equal to 1, nothing is changing. I'm saying this shape is 100% of the size that it used to be, which is all that it was before. My scale factor is 0.2, right? Again, if I multiply that factor by 100, that's how I get my percentage. And so it's 20%. Right? It's 20% of the original size. Now, how do I find that new width and height? Well, again, I have my formula. Scale factor is new over old. Let's find my width first. Right, so width, I know the scale factor is 0.2. We want to leave it as the decimal, right? We don't want to work with percentages when we're in our calculations. I don't know the new size. That's my goal, to find out what is the new size after this scale. But I know my original. I know that I was 3.5 something's wide, centimeters, feet, who knows. If I want to solve for x, I'm going to multiply up this 3.5, right? I'm cross multiplying, or I'm multiplying both sides by 3.5. So 0.2 times 3.5 is going to tell me my new size. So I do that multiplication, and it tells me that 0.7 is x. I'm going to rename that to w, just so it's clear. So my width was 3.5. My width is now 0.7. And we should see it getting smaller, right? We were reducing. We had a scale factor of less than the original, right? 20%. Let's find my length now. Same idea, 0.2 is still the same scale factor. I'm always scaling all dimensions in the same amount, or else it's not scaled. I don't know my new length, but I do know my old length. I do know it was 2.75. Same idea, to solve for that variable on top, I'm going to multiply 0.2 times 2.75. And when I do that calculation, I get 0.55. Right, we didn't have units here, but we'd include them if we did. And so that's my new width and height. Right, it was 3.5. It's now 20%, or 1/5 of that for the width. Right, it was 2.75. It's now 1/5 of that, right? It's 0.55. Right, so it's about 20%, or 1/5 as wide and 1/5 as tall. Let's look at a couple of examples. Suppose you're an aerospace engineer. It is your job to design a new type of fighter jet, and you've already been given a model for it. So you have the model. You want to build the real thing, right? You have the drawing, the schematics, something like that. The actual jet is to be 50 times as large as the model. So that's telling us our scale factor. The dimensions of the model are as follows. The length is 3 feet, the width is 6 inches, and my height is 0.3 feet. I want to find the dimensions of the actual jet. So again, scale factor is, and here's the thing, I'm going to use the new over old, because in this case, the new is actually the real jet. Right? When I say scale factor is 50 times larger, I'm saying to go from the old to the new, I should be multiplying by 50. For us, that means that the old is the model and the new is the actual plane. Right? Because I need to go from old to new using that scale factor. Right? And if you're not sure, think about the context, right? Should I be getting larger, right? Is my scale factor a number greater than 1? Or should I be getting smaller? Is my scale factor a number less than 1? I'm hoping that an actual jet is larger than this model. My scale factor is 50, which means that my old measurement should be smaller than my new measurement. So let's work with this. My length is 3 feet. So my scale factor, right, is new over old. I know my scale factor. I know my scale factor is 50. My new length, I don't know my new length. How long is the actual plane? That's what I'm trying to find. Originally, I was 3 feet. I'm going to multiply 50 times 3. My length is 150 feet. My width was 6 inches. Here's the thing though. We want to make sure that everything is in the same units. Okay? I want my length in feet. I have my height in feet. My width is in inches. Wouldn't it be nice if I could say that that was 0.5 feet? Right? And again, we can use those unit conversions we've done in the past to convert that. Right? Or you might know that there's 12 inches in a foot, so this is half of a foot. Everything needs to scale by the same amount, so I have the same scale factor for all three of these dimensions. My width over 0.5, right? New being the actual plane, old being 0.5. I multiply 50 by 0.5, and my width is 25 feet. Right? While it would still work if I was in inches, right? I could still use the same scale factor. That means my answer would be in inches as well. Right? I want to make sure all my units are consistent. And for my height, 0.3 feet, same scale factor. I don't know my new height, but I do know my old. 50 times 0.3 is 15. So my height is 15 feet. Right, the trickiest part is making sure you know, is this value that I have going in the new spot, the old spot, or is it a scale factor? All right. Our particular Egyptian pyramid is 22 feet tall, but the length across the base is unknown. There's a scale model of the pyramid that's 2 feet tall, and it has a base length of 1.3 feet. What is the base length of the actual pyramid? So, my real pyramid, somewhere out there in Egypt, all I know is that it has a height of 22 feet. I want to know how wide the base is. I do have a model, right? A smaller model. I would hope you're not carrying around a whole pyramid. It is then 2 feet tall. And I know the base of the model. I know the width of the base is 1.3 feet. Because this is a scale model, every linear dimension has been scaled by the same factor. So whatever was used to turn 22 feet into 2 feet is the same thing used to turn my unknown value into 1.3 feet. So if I can find the scale factor for one dimension, right, if I know two matching dimensions, in this case height, I can use that same scale factor for any other dimension. So let's find that, right? Again, I need to know scale factor. And in this case, it's up to you, really, which one you're considering new and which one you're considering old, as long as you're consistent. Let's say we're scaling down. I'm going to go from the real pyramid to the model pyramid. So my new measurement, my model, has a height of 2 feet, whereas the original has a height of 22 feet. So my scale factor is 1 over 11. Right? The model is 1/11 of the height, which means it's 1/11 of the width. Right? Or as a decimal, it's 0.09. So I have my scale factor. Now, let's say, okay, let's scale that width. I know my scale factor is 0.09. I need to make sure I'm consistent. I had my model on top. So I need to keep the model on top. If I switch that, now my scale factor is incorrect. That scale factor only accounts for going from the irregular to the model. So in this case, my unknown, my width of the real thing is actually my x on the denominator. So how can I isolate x when it's on the denominator? Well, my first step, I usually like to multiply the x out of the denominator. So I have 0.09x equals 1.3. Now I can divide both sides by that scale factor. Right? If you're trying to work backwards, notice that a lot of the time when we were finding the scale factor, we were multiplying. If Here we're going to divide because we're trying to go backwards. We're trying to say, I know the end result. Where did I start to get here? So I do 1.3 divided by that 0.0909. And I get about 14.3. And it was in feet. All right, so a scale factor scales in all dimensions. Let's look at one more example. You are a detective assigned to work on a robbery of your local grocery store. The surveillance film shows the suspect standing next to the checkout counter. Describe a method you could use for finding out the actual height of your suspect. So what are you thinking? Well, if we can see, here's our suspect standing next to the checkout counter. Well, the suspect is gone, right? He's run off. I can't figure out how tall he is because he's no longer there. However, I can see on the screen, right, how tall is that counter on the screen. If I took a still, I brought a ruler up to the TV, right, and I know how tall that counter is in real life. I can go back out to the store and the counter is still there. Okay. We can use that idea of a scale factor to say, well, if the counter has been scaled up by this amount to go from the video to real life, the suspect will have been scaled up by the same amount. Right? So as long as you can find the scale to original, as long as you can compare that model and original for at least one object, right? The whole video footage, everything in the store should be scaled up or down by the same amount, right? So with that, there's some practice here for you. I want you to give it a try. We have one more topic in our M23 unit. We're going to talk about 2D and 3D scale factors in the next video.